Okay, we're going to stay in the North Atlantic for a very complimentary talk. And our last speaker before the break, for real this time, is Mariona Claret from the University of Washington.
Well, thanks all for coming. Thanks to the organizers for inviting me here today. I want to start with this picture that we already seen. This is the Schmidt-Co oxygen decline inventory over the last 50 years. And it has been already said that when integrated over the whole water column and global ocean, our ocean has lost about 2% of the oxygen over the last 50 years. However, when we look at the map, this decline is actually very patchy. And at the local scale, the oxygen decline can be very dramatic. This dramatic deoxygenation has undergone in a region of high economic and environmental interest, which is the Northwest Atlantic Shelf. And in this area, there is the largest estuary in the world, the Gulf of St. Lawrence, where one of the longest deoxygenation time series has been recorded over the last 70 years, representing about a reduction of about 50%. So here I'm going to talk about how this oxygen decline in the coast and occurring locally occurs due to a remote process, and that is due to a shift in the large scale circulation of the North Atlantic. So this is a collaborative effort that I started as I was a postdoc with Eric Galbraith. And I had the pleasure to work as well with Jamie Palter, and Daniele Bianchi, Katia Fennel, Denis Gilbert, and John Dunn. So I'm going to start by describing a little bit the dynamics of this region. So this is the Gulf of St. Lawrence. It's characterized by a deep channel about 250 meters deep, the Laurentian Channel, and this is the Scotian Shelf. So in this region is very close to the subpolar front, where actually two very important currents in the ocean meet. This is, on the one hand, we have the Labrador Current that flows along the shelf edge, carrying oxygen-rich waters and cold towards the equator. And on the other hand, we have the Gulf Stream that flows in the opposite direction, carrying warm and oxygen-poor waters. So these two currents influence the slope water of the system, which is very complex, but is that system that ultimately influences and feeds the water for at the bottom of the Laurentian Channel, and also at the bottom of small basins in the Scotian Shelf that are connected through deep seals to the slope water system. And it's actually in these two regions, the Scotian Shelf and in the middle of the Gulf of St. Lawrence, where these dramatic oxygen declines have been recorded, either on an isopignal that is isolated from the atmosphere or a depth below the mixed layer depth. And part of about the deoxygenation trend in this time series is actually one order of magnitude larger than the deoxygenation trend occurring in the open ocean. And half of this oxygen decline is due to the oxygen saturation concentration decline, and this is the concentration that waters have when are fully equilibrated with the atmosphere for a given temperature, and to a less extent for a given salinity. So one of the remaining questions of this work was actually how much is this oxygen decline due to local process in the area versus how much is due to the larger scale climate forcing. So then, to answer this question, we look at a climate model developed at GFDL. It has an ocean component at 1/10 of a degree resolution, which is strongly adding, and you can see here in the sea surface oxygen, where the two currents meet, the Labrador Current oxygen rich in red, and the Gulf Stream oxygen poor in blue, when the Gulf Stream actually becomes unstable and developing meanders and eddies that are fully resolved in this simulation. So I want to stress this is a very unique simulation, a huge effort from GFDL. Its fully coupled global model. It took about 9 months to run 400 years using 10K processors. So the experiment went as follows. There was a spin-up at pre-industrial atmospheric levels of about 200 years. Then the simulation was branched into one control that kept those pre-industrial levels, and a warming case scenario of a CO2-driven warming at, by increasing CO2 at a 1% annual rate. So this model is suitable for our question because it reduces a warm bias that is known to be typical of coarse resolution models. This is illustrated here with sea surface temperature. This is the absolute value. Then typical CIMIC 5 models at 1 degree resolution show this warm bias in the Northwest Atlantic shelf. And is it because these coarse resolution models resolve the coastal separation of the Gulf Stream too far north of Cape Hatteras? And when we increase resolution, we actually see that the location of the Gulf Stream coastal separation is much more realistic, and this results in a reduced warm bias in this region. So what we do is we sample this model output in the same way and analyzing this in the same way as observations. And then we construct time series by time stretching the model year by a factor so that the PCO2 levels in the model and matches those from the observations for a given year. Then we extract the model output where the oxygenation time series were observed, and also at the mouth of the deep channel in the Gulf of St. Lawrence, where there exist very long hydrographic records as well. And we compute changes. Observations here are shown in dots, and changes are computed by subtracting 10-year mean from the 10 initial years of the time series. Then from the model in solid lines, the changes are relative to the control case scenario. So we observed that the model unfortunately did not capture the decline in total oxygen, but it did, however, reproduce very well the decline in oxygen saturation concentration. And this was associated to an increase in temperature that also agree well with the observations, and an increase in salinity. So this is an indication of a change in the water masses of this region. So then, to look where this change in water masses occur, we zoom out in the model and look at the oxygen on the same projected on the same isopignal that the decline was observed here in the middle of the deep channel of the Gulf of St. Lawrence. So on the left, this is the control simulation. On the right, this is the idealized warming case. White areas where the isopignal outcrops. This gray shade is actually the 200-meter isobath. So I'm going to show a 5-day time frame movie. First, I would like you to focus on the control case scenario. We see the Labrador Current in red that flows towards the equator and reaches its more southern point here. This region is Grand Banks, and this region is the tail of the Grand Banks of Newfoundland. Then, when it reaches this point, in order to keep following the edge shelf, it's forced. The Labrador Current is forced to do a sharp turn towards the right, which results in a ventilation of this area, which you can see with a clear supply of oxygen in the deep channel of the Gulf of St. Lawrence, and also. Sometimes here you can see a small supply in the small basins when there is through these deep seals. Then when we look at the warming case scenario, we first see that there is that the isopignal outcrops actually a bit farther north of the tail of Grand Banks relative to the control case. But most striking is that the supply of oxygen west of the region of Grand Banks is very much reduced, which actually cuts the oxygen supply to the Gulf of St. Lawrence and the Scotian Shelf. So this is indicative of a shift in the circulation, and we want to quantify this shift. And to this end, we look at the Motherstring function. This is a measure of the strength of the circulation and its rotation. So negative values means that this is a subpolar cyclonic circulation going anti-clockwise. So this is the Labrador current flowing this way. Then it does the sharp turn at the tail of the Grand Banks and recirculates in this sense. Then on the other hand, positive values means anticyclonic subtropical circulation, and the Gulf Stream is just south of the zero contour line of the string function and flowing towards the east. So and this is the 200-meter isobath. And then when we look at the warming cases scenario, we first observe that there is a weakening of the Labrador current strength, and also there is a shift in the zero contour line, which becomes closer to the Grand Banks, which meaning this is a great impingement of the Gulf Stream in this region. So this is consistent. These two shifts in the circulation, these actually result in a reduced transport of oxygen from Labrador current waters towards the west in this region. So, well, then that was all from modeling. Then we asked whether this was observed in nature, and Jamie came with this nice idea of looking at Hydrobase 3 database, which is here maintained quality control and maintained here in Woods Hole. And then we look at the depth of the isopignal at the same isopignal where the oxygen decline was observed in the Gulf of St. Lawrence. And the reason for doing so is because this isopignal shallows significantly, about 700 meters deep, when we move from subtropical waters to subpolar waters. So what we did is we focused in the tail of the Grand Banks, then we computed an anomaly to minimize the spatiotemporal aliasing, and then we observed, we constructed a time series with annual averages, and then we observed that since 1920, this isopignal has been deepening, with a trend that is statistically significant, and it agrees with what we expect, with the results from the model. So this means that there is an increase in buoyancy in this region, in this square, which is consistent with an increased presence of subtropical Gulf Stream waters, and which is consistent with a retreat of the Labrador current in this region. So then the ultimate question is how much of this large-scale circulation here contributes to the local oxygen decline in the Gulf of St. Lawrence and the Scotian Shelf. And to this end, we have decomposed oxygen changes in oxygen saturation and apparent oxygen utilization. So first of all, changes in oxygen saturation reflect a change in hydrography, here either due to a circulation shift that implies a shift in the water masses, or also due to warming that decreases solubility. We observe that the oxygen saturation change actually occurs west of Grand Banks, which is consistent with a circulation shift that reduces the oxygen supply in this region. Then we have the apparent oxygen utilization that reflects changes as well in ocean circulation, but in the water mass ventilation, and also in biological processes. So east of the Grand Banks, we know that the isopignal outcrops, and this decline in oxygen from a change in AOU is actually due to an increased stratification that cuts the oxygen supply directly from the atmosphere. Then west of Grand Banks, we know that the isopignal is isolated from the atmosphere, so that any change must be related to biological processes. Or as Jamie said, due to decreased transport of AOU using an N-member mixing model, which is actually what we did. So we did account, we know that this is for conservative tracers and AOU is not, so we did account for that. And we perform a 2 N-member mixing model here at the mouth of the Gulf of St. Lawrence with N-member 1, which accounts for subtropical Gulf Stream waters, and N-member 2 just east of the Grand Banks of Newfoundland, which accounts for Labrador current water. So we did the math, and you will have to believe me, I can give more details later, but we concluded that about 2/3 of this oxygen decline occurring here is because of a retreat of the Labrador Current, and the other 1/3 is because of a change in the end member of the Labrador Current, either to a reduced water mass ventilation or decreased solubility. So far, we have seen that the Northwest Atlantic shelf has gone a huge dramatic deoxygenation that is much, much larger than that occurring in the open ocean. We have used a climate model that actually reproduces this decline in terms of oxygen saturation concentration, and we have been able to explain that it's largely because due to a circulation shift that results in a retreat of the Labrador Current in this region, and this is because of a CO2 or anthropogenic warming ultimate cause. Then this mechanism likely happens in nature because we have also been able to show with centennial scale time series that the presence of Gulf Stream waters in this region is increasing. So now I would like to give some thoughts about the implications of this work. So first of all, we have seen that we have connected the oxygenation in this region with a change in oxygen offshore. And then the next question is what happens to the whole North Atlantic here? And so first of all, I want to say this is from model insight. So first of all, a recent Nature paper shown that the warming in this area using sea surface temperature is associated to cooling in the subpolar North Atlantic. And this dipolar SST pattern is actually related to a slowdown of the AMO. That being said, there is still very little evidence of this link in nature. So the other broad-scale impacts, my previous speaker already talked that CIMIC 5 climate models predict a decrease in oxygen in the North Atlantic interior due to reduced water ventilation of the Labrador Current in the Labrador Sea. Then also I want to stress out that changes in oxygen are also expected or predicted by CIMIC 5 models in the upper North Atlantic. And we have seen that the Gulf Stream is moving towards the pole, which we could expect that this extends to the North Atlantic currents, which carries subtropical waters in the open North Atlantic. And CIMIC 5 models actually show that the upper oxygen in the North Atlantic is going to be very sensitive to the location of the North Atlantic current and its strength. They don't agree, though, on how these changes, which are very patchy, are going to be. And finally, the obvious implications are for the local ecosystem. And under continued warming, we can predict more presence of subtropical warm waters, and this may ultimately threaten the life of benthic fish and marine invertebrates in the region. This has already been shown by Kathy Brennan, who projected the oxygen trends that I've showed you earlier. She projected towards the upcoming century and showed that oxygen levels start to be critical, for instance, for Atlantic wolffish, and will be very critical for the snow crab in the next decades. So here I'm finishing with summary implications, and if you would like to know more details, please have a look at our recent paper, and thank you very much.
My name is Ken Andersen from the Technical University of Denmark. I was just curious, you showed a lot of the changes in oxygen due to circulation. How, in your view, how important are changes in biological activity for the oxygen changes?
Yeah, I didn't stress on that part because the model does not reproduce, does not agree with observations, likely because we use a very reduced complexity biogeochemical model, which uses 3 tracers, and that's actually, that's a good question for the coastal deoxygenation. How we definitely miss coastal processes. We don't know where they are. Yeah.
In relation to the previous question, you do deconstruct how much is due to AOU, right, in the Gulf of St. Lawrence? Did I get that right?
Yeah, that's correct, from the model. Yeah.
Oh, that's from the model. That's not from observations.
That's not from,
okay.
Yeah.
All right, it seems like everyone is in need of some caffeine at this point. Oh, one more, thanks.
Samantha Sedlecki, University of Connecticut. I was just wondering how the results that you've presented here, how dependent they are on sort of the presence of the Gulf Stream, and how confident, how you might expect that to change within the various ensemble members, or how consistent they are in terms of their projections of the conditions of the Gulf Stream, you know, the presence and where its location is, you know, along the East Coast.
Yeah, that's a good question. I think all depends on how well the next generation models are going to resolve the coastal separation of the Gulf Stream. That, yeah, that's, you need very high resolution. That's, and fine bathymetry. I hope this answers your question. Yeah, that's the key point, actually.
All right, let's thank all our speakers for this session. And we'll try and meet back here at 11:05 so we can start our talks right at 11:10.